So while we've been waiting, I hope some of you have started to take a stab at this mechanism. I would not consider this to be trivial. Not because uh, you haven't had the principles, but because it's hard to make a decision here. It's hard to make a choice about which of two or three possible mechanisms is the right one. And um, you could see, how would you even start a mechanism like this? Well, maybe we can come back to this in just a little bit so we can talk about why it's such a challenge to make a decision about where to start your arrow pushing for this process. And it relates to the topic for today's lecture, which is acid-base arrow pushing reactions. And that just does not sound that interesting. Acid-base chemistry, you've taken a whole year of general chemistry, which was a lot of acid-base stuff, and the arrow pushing you'd think would not be that exciting, but we want to try to do the best job we can when we write out mechanisms. So let's come back to this interesting, I say, interesting chemical reaction. Most esters, like the lipids that form the cell membranes in your body, you'll also find ester groups in some metabolic intermediates like polyketide metabolism. They have half-lives of about 7 years. That ester bond has a half-life of about 7 years at neutral pH. So it's not a fast hydrolysis reaction. I'm not showing you buffered conditions like the inside of a cell here. I'm just saying if you put this in water, what do you think is going to happen under those conditions? There's clearly no good process if the half-life is 7 years. We don't go into the lab and run reactions that take 7 years, right? You would heat it, or you would dump in a catalyst or something like that. So why is this so challenging? So first, some of the things, how would you approach this mechanism? Here's what I would do. I would recognize the fact that I might want to think about protonating this carbonyl in order to make it easy for some sort of a nucleophile like water to attack, because let's just be real, water is a shitty nucleophile. Now, what's that going to attack? Maybe it could attack a carbocation, but beyond that, there's not a whole lot you could attack. And so maybe the first step ought to look something like this. Maybe we should protonate that with some sort of an acid under our reaction conditions. Maybe that's where we ought to start this mechanism. Or maybe we can just acknowledge the fact that there's a lot of water. Okay, water's a lame nucleophile, but maybe we can just use the water to attack right off the bat. There's plenty of water. If I give you a glass of water, if I give you a 1 liter bottle of water, that 1 liter bottle has 55 moles of water in it. So pure water is 55 molar solution of water, molar concentration. There's a lot of H2O in there. So do we need to protonate the carbonyl first? How do you decide about stuff like that? Or are the conditions acidic or basic if we're going to use symbols for proton transfers? Well, how would you decide whether the conditions are acidic or basic? I told you we're putting this into neutral water. Or no, I didn't say neutral, just water. Right? If you measure the pH of water coming out of your tap, it's unbuffered. It'll be all over the map. Here's what I see. I look at the product here for this reaction, and the product is a carboxylic acid. At the end of this reaction, you will have 1 mole of carboxylic acid in there. The conditions are acidic. There's no question here. The conditions are not basic. As soon as you start to generate product, you're starting to generate carboxylic acid. You can kind of see that the other product is not a base. The other product of this reaction is just the hydrolyzed alcohol. In this case, it would be phenol. So the conditions are acidic. You don't want to use B and HB as your symbols for proton transfer. I wouldn't count you wrong if you did, but it just, right, if you know the conditions are acidic, why not use the symbols HA and A minus? Maybe it'll clue you in. So this makes it a challenging mechanism. We don't really know, right, is the first step to protonate the carbonyl and generate a teeny tiny amount of this protonated carbonyl that's now easier to attack, or do you just attack with neutral water? And so we don't teach you enough to know which of those two scenarios is right, is the real answer. They're both plausible based on what you know. And so let's go ahead and keep talking about this interesting situation that you're going to face as you draw arrow pushing, where it's like, wow, I've got two mechanisms, they both look plausible. It's the end of the world. That's not the end of the world, right? If they're both plausible, then either one is okay. So sometimes you can't know in these cases of proton transfers. But notice how quickly we dismiss the idea of base catalyzed processes. You don't want to draw hydroxide anion. being generated by base and then attacking things under these conditions. Now, I want to bring you back to the first lecture that we had. I drew out this transformation, a very simple substitution reaction where I said, well, how would you think about the substitution of this hydroxy group for an amino group? And it's a deceptively simple looking transformation, but the arrow pushing mechanism is actually quite complex. And it's a pretty typical mechanism, arrow pushing mechanism. Your goal is to break down the mechanism into elementary reaction steps with a single transition state. And as you walk through this mechanism, the first step is taking this proton off of this cyanohydrin group, the OH of a cyanohydrin. That's a proton transfer step. And when you draw out most mechanisms in this class or in your introductory organic chemistry class, what you'll find is that they are dominated by acid-base proton transfer reactions. Here's another acid-base proton transfer reaction. Cyanide was a leaving group, and we're going to use the cyanide as a base under these conditions to pull a proton off the ammonium ion so that it can now act as a nucleophile. Here's another proton transfer. You generate this deprotonated carbanolamine, this Switter ion, and you have to protonate the OH to turn it into a leaving group. You protonate it with the acid, and then you pull a proton off over here, another proton transfer, so that you have a lone pair on the nitrogen. And then you have to turn that OH into a good leaving group, so now you turn it into an H2O+. Another proton transfer. There are proton transfers all over the place in this mechanism. So given the preponderance of proton transfer steps in arrow pushing mechanisms in this class and in introductory organic chemistry classes, it makes sense for us to think a little bit deeper about proton transfers and how do we decide whether those are plausible or not. What are some of our tools? I want to come back and talk about reactions here. So proton transfer events, when I talk about attacking H with some sort of a conjugate base or some sort of thing with a lone pair, right? I'm going to use the word proton. I don't call it a hydrogen atom. I don't call it a hydride. I call it a proton. So when we're doing simple acid-base reactions, refer to that H as a proton. And we don't, again, hydrogen atom means radical chemistry, and hydride is a completely different kind of species. So I want to compare these two processes. In both of these processes, if you draw an MO diagram, might seem similar, but they're not similar in terms of how facile these reactions are. So here's two things that are bonded to fluoride, to fluorine, and in both cases we can come over here and attack and then break the bond. That means in both cases we're adding to the sigma star orbital. We're adding to the sigma star orbital in both cases, but these are not equally good. I want to remind you that that hydrogen atom, the hydrogen is a first row atom. It is light. There's no lighter atom than a hydrogen atom. That means it vibrates very quickly. And if it vibrates very quickly, just look at an IR spectrum, you'll get the vibration rate is massively faster than a carbon-fluorine bond. Because it vibrates faster, it's easier to break. So hydrogen, acid-base reactions. Oh, sorry, let me change this. Let me try to erase this. I apologize if you wrote what I wrote. When I attack carbon, I don't like to use the symbol B. Use the symbol nu. That's a nucleophile. We don't call it an acid-base reaction if you're attacking carbon. We call that a nucleophilic attack if you attack carbon. So, it wouldn't be, if you're just doing arrow pushing, I'd forgive that. But I like to be very specific. If I say nucleophile, you're not attacking a proton. If I say base, you're attacking a proton. Yes, question?
So in the mechanism, there's a lot of proton transfers, but some of the steps are also like lone pairs forming a double bond.
Yep.
Is that like as fast as proton transfers, or is it slower?
We'll have to talk more about that. So we're going to get to this. So the question is, what about these steps where you form double bonds? Like here, you push down and you form a double bond. You're attacking sigma star when you push out that OH2 group. So is that faster or slower? The thinking that we'll give you later on as we go throughout this course is, wow, that's intramolecular. And that means this lone pair right here doesn't have to go anywhere. It is always donating into that sigma star orbital. It has a natural advantage. So what's faster, reactions of a first row atom like H that's so light, or that displacement? Depends on the leaving group. And in this case, I couldn't actually tell you which is faster. My bias is to say the proton transfer in this case is faster than that double bond forming ionization reaction. Okay, proton transfers, fast. Attack at carbon, slow. SN2 at carbon, relative to proton transfers, slow. Attack at carbonyls, slow. Proton transfers, fast. If you get anything from this lecture, I hope you'll think about the thing you would get is that don't be afraid to draw proton transfers. They may lead you down a mechanistic pathway that's not productive, but still they're happening, whether you draw it or not. So you're not crazy to draw proton transfers as you're trying to figure out mechanisms. Okay, let's go ahead and talk about how we're going to depict proton transfers. We're going to depict proton transfers like this. It's pretty simple. You take the arrow, you attack the H, you break the H bond to whatever in this case, the quote-unquote acid would be an HN bond. This is not really correct. I'm going to give you a little bit of honesty, but I will keep coming back to the fact that in our class, we are going to draw proton transfers as a single step with a single transition state. But let me be real with you about the real mechanism for proton transfers, even though we're not going to depict it for arrow pushing. The first step in proton transformation is actually formation of a hydrogen bond. This H likes to get close. The oxygen likes to get close to that NH. There's partial positive charge on that proton, partial negative charge on the oxygen. And so I'll go ahead and draw out that hydrogen bond. Oftentimes we draw these dashed lines. But I told you, we can't use dashed bonds for arrow pushing. You'll end up with the wrong charges. This is the first step in a proton transfer reaction, is formation of a hydrogen bond. So that H bond right there is definitely forming. But we're not going to use arrow pushing for that. I'm not going to draw it anymore. I'm just going to expect you to remember, yeah, there's some hydrogen bonding going on there. But this is Manfred Eigen won the Nobel Prize for working out the ultra-fast kinetics of proton transfers. And this was one of the outcomes of that. You initially form a hydrogen bond, and then as that H vibrates between those two atoms, at one point it's close to the N, at another point it's close to the H, it keeps vibrating, and eventually when they dissociate, the H ends up attached to one atom or the other. So that's the way proton transfers work. But we're not going to depict that with arrow pushing. We're just going to make it look like an SN2 displacement, this one-step process. This is the way we're going to depict this in our class. It's just a single, simple step. So why am I showing you this proton transfer if we're not doing it for arrow pushing? Because once you recognize that hydrogen bonds are important, it imposes limitations on what geometries are good and which proton transfers are plausible and which proton transfers are not plausible. So if hydrogen bonding is important, even though we're not going to draw it with arrow pushing, let's go ahead and talk about hydrogen bonds. What is a good hydrogen bond? So very simple idea here, and that is that the ideal hydrogen bond is linear. The bond between the base and the H and the acid component A, that bond should be linear. Protons vibrate in straight lines. Vibrations occur in straight lines. That should make we shouldn't have to explain that or go into deep detail. That H wants to vibrate back and forth between the O and the N in a linear direction. You would never see an H preferring to vibrate back and forth through 90-degree angles. They don't, like maybe if you're tossing a ball to somebody, it would go through an arc, but that's not the way hydrogen bonding works. So what does that mean? It means if you try to do a proton transfer through a 90-degree angle like that means that's insane. You can't. You're not going to make a good hydrogen bond. You can make a lame hydrogen bond, but you couldn't make a good hydrogen bond through a 90-degree angle. That doesn't make sense. When we transfer protons in this class, we're not going to transfer them through four-membered ring transition states. That just is not consistent with anything we know. So here, we already talked about this, but here is the way we're going to do proton transfers when we have these kinds of tetrahedral intermediates, or enols, or enamines. So let's go ahead and talk about what that's going to look like. So for us, when we do these proton transfers, let me redraw that same species here. This same species, this tetrahedral intermediate. It looks like it's an intermediate in an acetal forming reaction. Probably you had some sort of an acid species in your solution. There's protons on there. And if you're careful when you draw your mechanisms, you'll realize, oh yeah, there's probably an A- counterion still floating around. Maybe in step 1 I protonated a carbonyl, but I've still got this A minus sticking around next to my positively charged species from the beginning of the mechanism to the end of the mechanism, from the first step to the last step. So if you got the A minus there, the key here for us to continue this reaction is we want to get a proton off of here and onto this OR group so we can use the OR as a leaving group. So how are we going to do that? We're not going to do the 4-member transition state. What we're going to do, and see how convenient it is that I wrote that A minus there, is I'm just going to pull the proton off because I just told you that that ought to be fast. And where did that A minus go? Well, now it's HA. Look at this. It's right there, right where I need it to be. So how am I going to get the H onto the OR group? Well, it's the HA is right there. See how easy this is? And I'll pull that the proton off. And so now we've got our alcohol, ROH, ready to act as a leaving group. Just ready to go away. We would call that an oxonium ion when you have 3 bonds. And of course, I'm not going to draw the next step, but of course the lone pairs on that other O have just been waiting for its chance to push out that protonated alcohol. And those lone pairs on the other oxygen are right there. Okay, so this is the way we're going to transfer protons in this class. We're not going to use 4-member transition states. 5-member transition states, not so bad. 6-member, not so bad. Linear, perfect. So, so just don't transfer protons through 4-member transition states. It will always be faster to do this through an intermolecular proton transfer. Pull the proton off, come back, and put the proton back where you wanted it to be. And you may think, well, that's a lot of steps. I can't draw that. Yes, you can. Of course you can. That's what you have to do to get a good grade in this class, is draw the real steps that are occurring as opposed to some shortcut that's not plausible. Okay, so geometry is important. Avoid that 4-member ring proton transfer. Geometry is clearly important in determining which acid-base proton transfers are plausible. But the other obvious thing that is important is understanding which things are acidic and which things are not acidic, which things are basic and which things are not basic. And so we're going to refer to pKa's to help us figure that out. And so let's go ahead and talk about how you should use pKa's to think about proton transfers in organic chemistry. And we're going to shift gears a little bit from thinking about arrows. I'm not going to think about curved arrows so much as I want to think about equilibrium ratios, populations, concentrations. This is getting down to the heart of kinetics, and we don't do a lot of kinetics in this class, but kinetics means you keep track of the concentrations or the populations of molecules. That's what kinetics means. Okay, so I'm going to remind you of something that just took me decades to figure out, and I'm sorry you haven't had decades yet, but this took me decades. Low pKa means high acidity. And you're probably saying, oh yeah, I knew that. But when I'm flying along in my lecture spitting out pKa's at 100 miles an hour, it's kind of hard to remember that. And it's the opposite of what you would expect. You would think that because pKa's are designed to tell you about acidity, you would think that high pKa tells you high acidity. It doesn't. It's the exact opposite. It took me years. Like, why? Right? That doesn't make any sense to me. And I'll explain in a second why it's worse if you're an organic chemist like me. So the converse of that is that high pKa, it's not really exactly the converse, means that the conjugate base, that's another word that always kind of threw me, the conjugate base from that acid, A minus. If you've got high pKa, that means that the conjugate base is basic, is highly basic. High pKa means the conjugate base A minus is highly basic. So let's go ahead and put some numbers in here. Does anybody here know what the pKa for a hydronium ion is? I don't know if they cover that in freshman chemistry. Yeah, it's minus 1.7. That's great. I'm so dumb I can't remember that. So I'm just going to write minus 2 here. But I remember the minus 1.7 when I want to flex some memory muscles. There's a couple, like pi out to 12 digits or something where you're still trying to figure out how to use that. Okay, when you draw a proton transfer event, usually you don't draw the equilibrium arrow because I say, show how you get from starting materials to products. And I just want you to write forward direction reactions. You don't have to draw equilibrium arrows for this. But I just thought I'd draw the equilibrium arrow to show that this is in equilibrium. When you want to figure out the populations of molecules, and this is what you're always interested in, is the relative populations of each side of the equation. So what you want to do is you want to look at what is the acid on each side of the equilibrium arrows. So I've already identified the hydronium ion, this oxonium species, as pKa minus 2 over here. And so what's the acid on the other side? Well, if I'm generating this, the acid must have been this NH bond. So I want to think about the NH bond over here. And what's the pK of that? That's maybe is not so obvious. We're going to talk a little bit about that shortly. But I'm going to use a pK of about plus 38 for that. My gosh, minus 2 versus 38. Those numbers are really different. It ought to be easy for us to tell which of those two species is more acidic, the ammonia NH or the hydronium OH. The hydronium is more acidic. It's got a lower pKa. Hydronium is more acidic. Lower pKa, more acidic. You might have known that for some other reason, maybe because you did a lot of arrow pushing reactions using H3O plus as your acid. Maybe you knew that was acidic there. Maybe you know ammonia is actually a base. But when I look at those pKa's, this is an easy decision to make about what's base, what's acidic and what's not acidic. Now, 100 years ago, 150 years ago, there just were not a lot of reagents available in organic chemistry. It's like your reaction didn't work, you dump in acid. Oh, I got a bottle of nitric acid in the lab or sulfuric acid, let's dump in some acid. Oh, it's not going, add some HCl, we'll add acid. That was the solution 100 years ago. But once in organic chemistry we figured out how to do reactions under anhydrous techniques, under nitrogen gas that's dry, we could start using super basic compounds. Instead of dumping acid into every reaction to make it work, we suddenly realized, whoa, we can make super basic compounds that aren't stable in air. And so now, as an organic chemist, and this is probably for the past half century this has been true, we care less about acidity and we care more about nucleophilicity and basicity. All of this information with pKa tables and acidity is kind of old, last millennium thinking. In this millennium, we care about what's nucleophilic. Because I care about forming carbon bonds, I care about nucleophilicity. That's the thing that really drives modern organic chemistry. Not even modern organic chemistry, chemistry from 50 years ago. So now we do everything under nitrogen gas. We exclude water, water vapor, air you're breathing is full of water, and we use super strong nucleophiles. Now, how do you use pKa's? That's kind of all we've got. We've got tables and tables and tables and books of pKa's because anybody can do a titration. I'll bet everybody in this class has done a titration before, an acid-base titration. We've been doing those for 2 centuries, so we've got lots of pKa tables. How do we use those pKa tables to tell us about nucleophilicity? Let me draw an equilibrium here, and I'll do it with water, but that would be an atypical scenario. So I've got some sort of an equilibrium process here. How do I think about nucleophilicity? What I'm going to do is I'm going to identify the acid on each side. So it looks like we're transferring this proton over here, and then we're putting it over here on this water molecule to make that same hydronium ion. So the pK on this side is the same. It's pK minus 2. And what's the acid on the other side? Well, it's that acetylide, the terminal alkyne, the terminal triple bond CH. And that has a pKa of about 24. Now, when you took if you take an introductory organic chemistry class, they tell you about the acidity of these CHs. They would quote you a number, 24, 25, somewhere in that range, to tell you something about this. And this tells you a lot. So, so remember, higher pKa means the conjugate base, or the conjugate base you generate is more basic. So here's what we're going to do: is we're going to introduce a new type of. It may not be new for you. You may have already heard of this. We're going to introduce something called pKa because we don't really care about acetylene. We're not ever going to use this bond to attack anything. So why should we care about the acidity of that? What we care about in this class and in the field of organic chemistry is the conjugate base. That's what we care about. And so we want to talk about that species, not the acid on the other side of the equilibrium. And so what number do we use to describe this? I can't use the word pKa to talk about this because there's no proton on it. You can't use the word pKa or the number pKa. So somebody invented this other variable they call pKa prime. That means if you put a proton on there, what would the pKa be? And in more modern organic chemistry, people use pKHA, because then it's more clear that what you mean is if you put an H on there, what would the pKa be? And it also, sometimes the prime is kind of hard to see. So we have this thing called pKa prime, pKHA, and the pKa prime for this acetylide anion is very easy. It's just the pKa if you had stuck a proton on there, and it's still 24. If you know the pKa when it's got a proton, then you know the pKa prime. And the pKa prime for water, what would the pKa be if you stuck a proton on water, is -2. So if you've memorized the pKa's, then you know the pKa prime for the conjugate base. And the generality that we use that's quite powerful. This is the one we use for modern organic chemistry, is higher pKa prime means you've got a stronger nucleophile. And that's usually what we care about in this class. We care about nucleophilicity, making bonds to carbon, right? That's what we care about in this class. We're just not that interested in doing acid-base reactions for a whole quarter here. So we want to talk about making, and so now when I look at these two species, which of these is more nucleophilic, H2O or acetylide anion, and I look and I see the pKa prime is way higher, higher pKa prime means higher nucleophilicity. This is more nucleophilic because the pKa prime is higher. That's what I care about. It's more nucleophilic, not by a little, by 26 orders of magnitude. Not by a billion, not by a trillion, not by whatever the other higher numbers are that are higher than a billion, I don't know. I mean, if you said it was a billion times more nucleophilic, it'd be okay, I get it. Right? But there's bazillion, we'll call that. It's a bazillion times more nucleophilic. If you're starting to make bonds to carbon by using that water molecule, you're missing the point here. You could have used a pK table to tell you that the acetylide anion is vastly, vastly more nucleophilic. Okay, so where did I get those pKa's from? I got them from this table, and you're going to have to memorize every pK in this table. So that way when we talk, when I'm talking in lecture about which is more nucleophilic, which is more acidic, we have a common language that we can discuss. And it's not simply, right, if I just ask you to remember these numbers, there's only a few in here that are really going to stick with you. What I really want you to know is the trends that go along with these numbers. So let's walk through these trends, these 6 types of trends that I've identified that have to do with things like electronegativity and resonance. Because if you know the trends, you can go beyond this table and say this one is more or less acidic. This one is more, or this conjugate base is more or less nucleophilic. These are all aqueous pKa's, which is not ideal. Aqueous pKa's give you information that correlates with nucleophilicity. It's not a perfect linear correlation, but really these are all based on a simple titration equation that you should have seen in your introductory chemistry classes, in general chemistry classes. It's defined as the pK if you put it in water, even though some of these weren't actually put in water to determine these numbers. Let's start off with looking at the effect of electronegativity on how acidic H's are. So if we look at these H's right here, attached to carbon, attached to nitrogen, attached to oxygen in these cases, look how much different in acidity these numbers are. The differences are absolutely insane. How many times more acidic is this ethane versus the methylamine NH? 10 to the 14, 14 orders of magnitude. That's more than a trillion. It's some number, it's 10 to the 14. It's huge. At equilibrium, if you put an anion in there and let it equilibrate, at equilibrium you'd have 10 to the 14 of one conjugate base and 10 to the 1 of the other. So it's very hard to make ethyl anion, free ethyl anion. In fact, we don't have ways in modern organic chemistry to make a free ethyl anion. Whatever you drew in your organic chemistry class is not real if you drew a free ethyl anion. It would be a completely insane species. So sometimes to rationalize acidity, you have to draw out this equation. Sometimes acidity is best explained by the relative stability of the conjugate bases. Sometimes you can just look at the acid and compare two things. But acidity is determined by both the instability of the HA and the stability when you put a lone pair and a charge on A minus. Okay, it's still a huge difference between making an N minus and an O minus, 20 orders of magnitude different, right? It's easy to make alkoxides and hydroxides. It is not easy to make amide anions. N minus, methyl amide anion, that would just incredibly hard. You need things like butyllithium or alkylithiums to deprotonate the NH of an amine. Now, if we put a pi bond next door, so if we talk about the acidity of CH, NH, and OH, but notice what we've done here, now we've stuck a pi bond next door to that. So when we make the carbanion, we get resonance. It's like an allyl anion. Allyl anions are stabilized by resonance. If we make an NH2 anion that's next to a pi bond, we have resonance. That would be an enamine anion. And if we make an OH bond and we put that next to a pi bond, well, if you deprotonate that, you make an enolate. And we'll talk a lot more about those. And immediately right off the bat, you can see it becomes, that CH3 becomes a lot more acidic when there's a double bond next door. That's resonance, right? The anion you would generate likes to donate into pi. You'll get stronger donation if you put a carbonyl next door. If you make an anion, right, by deprotonating that methyl and there's a carbonyl next door, that's another enolate. That's an enolate structure you would generate. It's way easier to deprotonate methyl when it is next to an ethyl, when it is next to a carbonyl. It is way easier to protonate an NH2 when it's next to a carbonyl. It's way easier to protonate an OH when it's next to a carbonyl. And in fact, it's so easy we call this a carboxylic acid. So, right, being next to a carbonyl, that's great resonance delocalization. If you're trying to stabilize an anion, put a carbonyl next door. That'll really make that anion stable, and it makes these OHs acidic. So I expect you to know that it's easier to deprotonate if you've got a carbonyl next door. You probably already knew that, but I'm giving you some numbers that will help you put that into perspective. All right, hybridization is so important, right? If I go from sp3 to sp2 to sp, right, the amount of S character, right, the amount of P character increases this way, increasing P, and the amount of S character increases going downward. And when you have anions, carbanions, lower energy orbitals are where you want to put those electrons. The more S character, the more stable those electrons will be. So if you have a lone pair, if you deprotonate one of these and make a carbanion, you want that carbanion to be sp hybridized if you're looking for stability. So this would generate this is the most acidic by a lot, most acidic, because the carbanion you generate is super stabilized. So that's the most acidic. Again, it's big numbers. These are huge numbers. 26 orders of magnitude, that's more than a mole, right? It's 26 orders of magnitude is massive. Don't get lost in the teeny tiny effects in organic chemistry. These big effects of hybridization, of electronegativity, of resonance are the ones you need to pay attention to. Now when we talked about MO, we talked about the importance of bond length. And bond length is really a function of going to lower rows in the periodic table. So if I look at the acidity of this OH functional group over here, an alcohol, pK16, you should know that. That's about the same as water. And I compare that to a thiol, where I'd simply walk down in the periodic table. If I walk down one row in the periodic table to sulfur, look, it's more acidic. It's substantially more acidic. Right? If you look at the relative acidities of the alcohol versus the thiol is 100,000 times more acidic. When you go inside of a cell, the most nucleophilic species inside of any cell are the cysteine side chains, the thiolate anions that exist. 1 out of every 100 or so thiols exists as a thiolate. So when an enzyme needs a nucleophile, it goes and it grabs a cysteine SH and makes an anion out of that. Much easier to deprotonate than an alcohol, and it's more nucleophilic when you do deprotonate it. Okay, let's look at what happens. I'm not going to go further with the trend down to lower atoms like selenium. That's not that common. But let's go over to the halogens so we can more clearly see for a common set of species what happens as we drop to lower and lower rows. Right? What's more stable, fluoride anion, chloride anion, bromide anion? I don't, maybe I don't want to get into that. Let's just look at the trend in acidities. You know, hydrofluoric acid, HF, that's just not that acidic. And it's not that common. We don't use that much in the lab because HF dissolves your bone, and it's kind of embarrassing if you, and it's hard to reverse once it soaks into your skin. So we tend not to use HF for a couple reasons, but mainly it's just not a strong acid. When you want a strong acid, drop down a row to chlorine. Hydrochloric acid is a strong acid by a lot. 11 orders of magnitude more acidic than HF. You really, this is the way to get high acidity. You don't get super big differences. I've never seen anybody, unless they wanted to make a carbon-bromine bond somehow, use HBr. That's, right? If you just need an acid, HBr is not worth the hassle. You don't get big-time difference in acidity by going HCl. And HI, similarly, if you just want a cheap, easy acid, get HCl. It'll do everything that the HI could do if you just need a proton from, and you're not worried about the counterion. Okay, so drop down from the second to third row, huge effect. Now charge, I hope this is kind of obvious to you, maybe, that if you compare the acidity of an NH and making an amide anion versus an ammonium cation and deprotonating that, it's a lot easier to deprotonate the nitrogen if the nitrogen has a positive charge. The nitrogen does not want to have that positive charge. Nitrogen's a little bit electronegative, so it's way easier to deprotonate. So when you look now at the pKa of this ammonium ion with that positive charge there, wow, that's more than 20 orders of magnitude more acidic because of that positive charge on there. Wants to get rid of the positive charge. Take the proton off, you'll lose the positive charge. And the same if you go from an alcohol, pK 16, to an oxonium ion, right? A protonated ether has a pK of about -4, about 20 orders of magnitude more acidic because of that positive charge. Protonated alcohols, very similar pK. Protonated hydronium ion, we already talked about that. That's got a pK of -2. Protonated alcohol is right in between, it's -3. So, you know, if you couldn't remember and you said -2, -3, it wouldn't make any difference for the kinds of things we do in this class. Those are all numbers that put you in the ballpark to be thinking correctly. We already told you that if you protonate carbonyls, it makes the CO easier to attack, right? It's easier to attack the carbonyl, but it's not easy to stick a proton on that carbonyl. And that's hard. It's hard to transfer a proton there. You need things like sulfuric acid or hydrochloric acid to really generate high concentrations of protonated carbonyls. Protonated imines are easy to make, and when you do, they're more reactive than neutral carbonyls. That's the whole field of organocatalysis is based on that idea right there. Okay, if you want to deprotonate water to make a hydroxide anion, that's just like the alcohol. It's no 16 versus 15.7. It's like there's no reason to know it to 0.1 decimal points. Now let's take a look at a slightly different situation, and this is sadly the one that the organic chemistry textbook Smith covers first and considers the most important. So if you put an electronegative atom somewhere near your OH, how much more acidic does that OH become when you put an electronegative atom nearby? There's no resonance here because there's a CH2 group. Right, there's a CH2 group right here. It becomes, that OH that I've highlighted is a little bit more acidic. You know, it's not a pK of 16, it's a pK of 13.4. That's about 2 orders of magnitude. Man, that's nothing. I mean, we shouldn't dwell on that. There's a slight effect there, okay. We're interested in 10 to the 20, 10 to the 30. That's the types of effects that are really going to help you think about organic chemistry. When you think about polar effects, electronegativity, sometimes they call them inductive effects. Those are kind of piddling small things. You can really amplify them if you go to the most electronegative element in the periodic table. That would be fluorine. So if I take acetic acid, which is very common, I had that up here. It's the same number. That's acetic acid. And I put one fluorine atom, that's the most electronegative atom. Okay, you can see a reasonable effect, a couple orders of magnitude more acidic when I take acetic acid and I put a fluorine somewhere nearby. The fluorine helps to stabilize the acetate negative charge when you deprotonate acetic acid. And if I put 3 fluorines, okay, now we're starting to see an effect. Trifluoroacetic acid is a pretty common reagent. That's about 5 orders of magnitude more acidic than just regular acetic acid. It makes it worth using trifluoroacetic acid. Never seen anybody use fluoroacetic acid where that was a useful enough effect to make it worth their time. Okay, so you need to understand the trends here. Electronegativity, huge effect. Resonance, huge effect. Hybridization, huge impact. Bond, or rho or bond length, huge effect. Those are the big effects. And charge is kind of an obvious thing. You know, if it's got a positive charge, you want to deprotonate it so it's got a neutral charge. It's not as big of an effect as these other things, that the charge aspect. Okay, you need to know these numbers because we'll refer back to these through our lectures. Okay, so you know, we're not going to spend our time in this class. I mean, hopefully soon we're going to get off talking about these pKs and just start drawing some arrow pushing mechanisms. And you'll frequently be confronted with reactions like this. It's like, okay, here's two reagents and here's the product. You can see there's a carbon-nitrogen bond in there. And what's the mechanism for this reaction? And the key to understanding this reaction is that they definitely throw in that they're doing this with sodium hydroxide. This reaction has special conditions. It's called a Schotten-Bowen procedure. We don't need to focus on that. But when you see something like sodium hydroxide, I hope everyone in here knows it's a base. You've probably done titrations and used it as a base in a titration reaction. So it would be perfectly natural for you to say, well, they're throwing it in, they're using it as a base. That means I have to take this hydroxide and use it as a base in step 1. We don't have any rule that says you have to use the base in step 1. That's not any rule in organic chemistry. So I want to talk about why this doesn't exactly make sense and what would be your guide that this isn't the best way to start off this mechanism. And I'm going to give you an equation that I expect you to know how to use. And the equation is just so intimidating. It scares me. I don't even know if I had to give you this equation. I don't know if I could spit it, but I know how to use this equation. So I'll teach you how to use this equation to think about populations in an intuitive way. And hopefully you'll forget the equation soon because, boy, I'm not good at working equations. Once I went into organic chemistry, all my math skills, my considerable math skills just kind of evaporated. Okay, so we're going to use this equation to think about this step. Is it plausible? Is it plausible to use a hydroxide base to deprotonate an amine so that we can make an amide bond? Well, this is an acid-base reaction, and I have pKa's that I told you have to memorize. Let's go ahead and draw out the pKa's for these numbers here. Right, the pK for this amine over here, this dimethylamine, or I forgot what amine it was. It was piperidine, I think, was the amine. Well, that's going to have a pK. The substitution on the amine slightly changes the pK. I'm going to use a pK here. Maybe I looked this up in a table. I can't remember whether I looked up the pK for piperidine or whether I'm using the pK for an amine from this table. You know, will it matter whether you use 36 or 37 or 38? I don't think so. You'll come to the right conclusion here with whichever one of those numbers. But this is the number for that piperidine compound. On the other side of the equation, what's the acid? We're just talking about transferring a proton back and forth, so we need to know what's the acid on each side of the equation. On the left side of the equation, it's that amine. On the right side, it's water. And so the pK for water, I hope you would know that one, that's got a pK of 16. Good enough for us. Okay, which of these is more acidic? Water's more acidic. Water's going to push the equilibrium over to this side. Water's more acidic. There you go. We know the direction of the equilibrium. We got two acids. Each one's trying to donate a proton. Stronger acid's going to win. So we already know the direction of the equilibrium. But what we don't know is what are the amounts of each of those species? Maybe there's just enough hydroxide in. Maybe even if the equilibrium lies over on this side over here, maybe there's just enough of this amide anion to be reasonable for it to attack. All right, so let's go ahead and try to think about some populations. And I'm going to use our secret equation here, this secret but powerful equation, to think about what that equilibrium constant and what the equilibrium ratios would look like. So I'm going to say KEQ is equal to 10 to the power of the difference in pKa's. That means I have to subtract the pKa's. And when I subtract those two numbers, you know, I can do this subtraction. There's only two numbers, right? The only thing you have to worry about is, right, which number comes first when you do the subtraction, and it's products minus reactants. Doesn't that sound familiar? It's like products, energies of products minus the energies of the reactants. pK of the product acid minus the pK of the reactants acid. So that means the equilibrium constant is 10 to the minus 20, right? It favors the starting materials, not by a little, but by a lot. Now, I don't know what to do with 10 to the minus 20. That number doesn't say anything to me. It's like I don't go to the grocery store. It's like, oh, I'm short some change. I need 10 to the 2.7 pennies or dollars here. Nobody thinks in the, what we think in is ratios. Let's convert that into a ratio. If it's 10 to the 20, that means at equilibrium, we already said it favors the starting materials. That means the equilibrium looks like this. 10 to the 20 of both hydroxide and amine for every one of water and amide anion. 10 to the 20 to 1. Right? That's crazy. I hope that's 20 zeros, but you get the idea. It's that many to 1. You know, in this reaction, it is more likely that this is going to be the nucleophile, not this amide anion where maybe about 1 molecule in your flask exists in that deprotonated form. That's not plausible that the amide anion is going to attack anything. Yeah.
So in terms of like identifying which direction the equilibrium lies, do you think it's more important to do the equation first versus comparing pKa?
I can't. I've been doing these so long. I don't even remember the order I naturally go in here. It's like my logical thinking is I look at both sides. The stronger acid pushes it to the other direction.
Okay.
Stronger acid will drive the equilibrium towards protonation of the other thing. Now I'm giving you a situation right here that is for organic chemistry. When you pour reagents into a flask, you pour acid into a flask, you pour sodium hydroxide into a flask, organic solvents. This is a different equation than you would use under buffered conditions. Don't use this in your chemical biology class because that's done under buffered conditions. But if you go into a biolab, everything is buffered. You control the pH, not the chemical reactions. When you go inside of a cell, the cell controls the pH, 7.2 to 7.4. The pH is controlled, and we use a different equation there. I'm not going to go through that. I think you've had experience with this. Under buffered conditions, right, you use the Henderson-Hasselbalch to determine the ratios of HA and A minus. Again, unless I write pH equals 3 and phosphate buffer, which is never in this class, then don't use Henderson-Hasselbalch. We'll use this simpler equation here. I want you to think about ratios of starting materials and products. Okay, we are just about out of time, but I'm going to stop here. I mean, this is just basically saying we're going to have lots of proton transfers in this class. And as you're transferring protons, no matter how long the mechanism is, I expect you to be thinking about proton transfers at each step and assuming there's an equilibrium ratio. And you should have an intuition whether that equilibrium ratio favors one side or the other for every proton transfer event that we do in every mechanism.